This is lecture 9. This lecture will be talking about electron configuration and orbitals. And we're going to start with orbitals, and specifically we're going to be talking about the nodes in orbitals. And the nodes are what give orbitals their unique shapes. So a node is a region with zero probability of an electron ever existing. And when we say zero probability of an electron, we mean an electron in a specific orbital or at a particular energy. For each orbital, there is n minus 1 total nodes. So if you're at an n equals 3 primary quantum number, then you're going to have 3 minus 1 or 2 total nodes. And we'll talk about that a lot. And there are two types of nodes. And the type of node that exists depends on your angular momentum, or L value. So there's a planar node, also referred to as an angular or axial node. And this kind of node is just a straight plane. So here it's drawn as a dashed line, and future slides I'll show you it's a plane, so like a sheet that cuts through the orbital. And the number of planar nodes in any orbital is equal to the angular momentum quantum number of that orbital, so L. The other type of node is a radial node, which is a spherical node that wraps around the nucleus at a certain distance from the nucleus. So the radial node is a sphere, and the number of radial nodes is equal to the total number of nodes minus the number of planar nodes. So since there's n minus 1 total nodes and there are L planar nodes, the rest are going to be radial. So n minus 1 minus L radial nodes. And from the shape and number of nodes, you should be able to identify the subshell that we're talking about and vice versa. So you won't always be able to pick out the specific orbital, but you should be able to figure out subshell. So let's start with s orbitals. S orbitals are always spherical. So on here I have the 1s, the 2s, and the 3s orbitals. And if you can look closely on this 3s orbital, you'll notice it's got a big sphere and then a little sphere or a medium sphere inside. And then in the very center, if your eyes are really good, you can see there's actually a third sphere in there. For the 2s, you just have a medium sphere and a small sphere inside, and then for the 1s orbital, you just have a relatively small sphere. So how many planar nodes are in an s orbital? Well, s means that we have an angular momentum of 0, so there are 0 planar nodes. Now, how can you tell different s orbitals apart? For that, you're going to have to look at the number of radial nodes that you see. And with s orbitals, it's kind of hard to see the radial nodes because they're all inside each other. So if I plot this a little differently, where for each of these orbitals I plot the distance from the nucleus on the x-axis, and on the y-axis I plot the distribution of the electron, or the probability of it being at a different place, you'll notice it's got a high probability of being really close to the nucleus and it falls out quickly. That's the 1s orbital. For the 2s, you have some small probability of being close to the nucleus, and then this dashed line right here indicates your radial node. And so then right here at this dashed line, electrons can't exist there. But we do have some probability of the electrons being beyond that point as well. And for the 3s orbital, we're going to have n minus 1 radial nodes, and those are denoted by these dashed lines. So if it's the 3s orbital, the 3 means n equals 3, and so we're going to have n minus 1 radial nodes, which would be 2. And those are denoted by these dashed lines. So if we go all the way up to a 7s orbital and ask how many total nodes there are, well, there's going to be n minus 1, which will be 6. And if we ask how many planar nodes there are, that'll be 0, because the angular momentum is still 0. And if we ask how many radial nodes there are, that's going to be total nodes minus planar nodes. So there's 6 left over for us to look at. All right, now let's talk about p orbitals. P orbitals, of course, have these 2 lobes, or dumbbell shape, as you'll often hear it referred to as. And why does it have this shape? It's because of its angular momentum, its L value. P in this sense means angular momentum of 1, which means that we have one planar node in our orbital. And that planar node, as you can see here, it's just like a sheet or a square that comes in and chops that orbital in half. So the p orbital is similar to the 1s or to the s orbital, except that planar node chops it into two halves. So then how do we differentiate different p orbitals? Well, it's going to be the same as we did with the s orbitals. We're going to look at the radial nodes. So we can tell it's a p orbital by how many planar nodes it has, and then we can determine which p orbital, or which energy level at least, based on the number of radial nodes. Since p orbitals have an angular momentum of 1, there are going to be n-2 radial nodes. So for a 4p orbital, how many total nodes do I have? Well, you have an n value of 4, and 4 minus 1 is 3. So you have 3 total nodes. How many are going to be planar? Well, this is still an L of 1, so you're going to have 1 planar node. And then how many are going to be radial? Well, I have 3 total minus 1, so I have 2 left to be radial nodes. So a 4p orbital is going to look like this, where you have these big bowls on the outside, these medium bowls on the inside, and then just little tiny pips on the inside. You'll notice this is all cut in half right down the middle. So it's divided basically in two, and that is our planar node. And then we have our radial nodes chopping these different regions out, cutting out the bowls from each other. The one way of figuring out how many radial nodes you have is by starting from outside, and then as you move in, see how many times the orbital changes color. So this one goes from gold to blue to gold, and it can be a little hard to see in this picture, but it goes from gold to blue to gold, so it changes color twice, which means we have 2 radial nodes. Another way of figuring out the radial nodes is by just trying to figure out how many circles are drawn in there that you can't see, or rather, how many circles are not there that are cutting these orbitals into pieces. Right, now let's go on to d orbitals. Right, and d orbitals have an angular momentum value of 2. So that means they have 2 planar or angular or axial nodes. Sorry, I wrote radial here on the slide, but it should be axial. So these cut your sphere into 4 lobes, right? If you think about starting with an s orbital that's a sphere, you put 1 planar node, now you're chopped into 2 pieces, then you send your next planar node through there, and that chops it into 4 pieces. It's like slicing a piece of pizza. You give it 1 slice, and a second slice, now you have 4 pieces of pizza. Now, the reason that planar node doesn't always work for this description, sometimes we have to use the words angular or axial nodes, is because of situations like the dz squared orbital right here, where it has these cone-shaped nodes. And so in this case, we have a top cone-shaped node and a bottom cone-shaped node. So this counts as 2 distinct nodes. Don't confuse those as being the same thing. And so these guys are pretty weird though, right? And so it's a little tricky to identify these angular nodes like this, but do your best. Now, how do you differentiate d orbitals? The same as you do with s and p orbitals, you look for the radial nodes. And since d orbital has an angular momentum of 2, you're going to have n-3 radial nodes. So for a 5d orbital, how many total nodes do you have? Again, you have an n equals 5, and so n-1 equals 4 total nodes. How many are going to be planar? 2. Why? Because d orbitals have an L value of 2. That's the definition of a d orbital. It has an L value of 2. Then how many nodes are going to be radial? Well, we had 4 total. We have 2 planar nodes, so all the rest are going to have to be radial nodes. So here's a picture of our 5d orbital. And in this one, it can be a little bit hard to see, but we have the orbital cut in half this way, then cut in half this way. Then we have one radial node here and a second radial node in there. So in this case, we're not really looking at a change of color. In this case, we have white as the electron density, and then black is the regions where the electron is not going to be. So it goes from white through black to white through black again. So it travels through that empty space twice. If you start from the outside and move in, you travel through empty space twice between regions of electron density, which means this has two radial nodes. The last orbitals we're going to be talking about are the f orbitals. And these also get their fun shapes from the planar nodes. F means that you have an angular momentum of 3, which means you have 3 planar nodes in our f orbitals. And so if you think about these getting sliced 3 times, if you think a piece of pizza, you're going to send 3 slices through it, and you're going to have 6 total pieces. And that's how many most of these have, though you can actually slice it kind of funny to get a couple with 8 lobes, and you get this one with the double donut. But these planar nodes are what are chopping up our f orbitals, and you differentiate the different f orbitals by looking at the radial nodes. And since L equals 3 for an f orbital, you're going to have n minus 4 radial nodes. So I could give you a problem like this and ask, what orbital is this that I'm showing you? Now, you wouldn't have to give me that xy minus z squared stuff, but you would have to be able to tell me what the n value is and whether it's an SPD or an f orbital. So let's look at this guy. Well, it looks like it was sliced once, twice, and 3 times. So if it's sliced 3 different times, that means that we're going to have 3 planar nodes. If you have 3 planar nodes, that means you have an L value or an angular momentum value of 3, which means you have an f orbital. And how many radial nodes do we see? Well, I see one right in the middle there, cutting the outer region from the inner region. Put another way, if I start from the outside and come in, I go from blue to gold 1 time, so I have 1 radial node. How many total nodes do I have? I have 3 plus 1, so I have 4 total nodes, and I know that I also have n minus 1 nodes in every orbital. So n minus 1 equals 4. If I solve that for n, I find that we're at the n equals 5 shell, and we have an f orbital, so this is a 5f orbital. Let's do a little practice to see how you're doing with that. Which of the following comparisons is true concerning the 3s orbital and the 3d xy orbital? You can go ahead and pause now and try and figure this out. All right, here's our options. A, 3s has more nodes than 3d xy. B, 3s has the same number of nodes as 3d xy. 3s has fewer nodes than 3d xy. D, cannot be determined. Or E, all of the above. Well, these options are just talking about nodes, not specifically radial or planar nodes. And so everything at the n equals 3 level has n minus 1 or 2 nodes. So the answer here is B. The 3s and the 3dxy have the same number of nodes. The big difference is that the 3s orbital has 2 radial nodes, whereas the 3dxy orbital has 2 planar nodes. Why do we care about this? Well, as we get farther into this, we're going to find out that chemical reactions and bonds all depend on electrons, where they're at. And so knowing where they're at is going to let us figure out how things are going to react, what orbitals are going to interact in one atom with the orbitals in another. Now, I've shown you this slide before. Now we're gonna start talking about electrons going into these orbitals. And you've seen this data here before for a hydrogen atom, where these are just the orbitals we get from solving the Schrodinger equation. And for a hydrogen atom, the energy only depends on n, a hydrogen atom with 1 electron. So what that means is going from a 1s orbital to a 3s orbital is going to take the same amount of energy as going from a 1s orbital to a 3px orbital. The S, or the 3s, the 3p, and the 3d orbitals then are what we call degenerate, meaning they all have the same energy. So the same photon can excite an electron from the 1s orbital to the 3s orbital, as can excite an electron from 1s to the 3pz orbital, or whatever. However, when you get into a multi-electron atom, this picture actually changes a bit. The big difference is that in multi-electron atoms, the core electrons, the ones down at 1s and in 2s, etc., will actually repel the outer electrons. And what that does is causes the p orbitals to be slightly higher in energy than the s orbitals, and the d orbitals to be higher in energy than the p orbitals. And so now we have to figure out how much energy it takes to get into each of these orbitals. And the general rule is that the energy of an orbital increases as n plus L increases. So as your primary quantum number and your angular momentum. So what that means is for a 3s orbital, you have an n value of 3 and n value of 0. So this has an energy value of 3. And for these d orbitals, you still have an n of 3, but you have an L value now of 2. So your energy value would be 5. All orbitals now in the same energy level are not degenerate. So now the 3s is not degenerate with the 3p, but all of the 3p orbitals are degenerate with each other. All of the 3d orbitals are degenerate with each other, the 2p also. So now going from the 1s orbital to the 3s orbital is going to take different energy than going from 1s to 3px. You're going to have to absorb a different photon of light, though it's going to be a very similar wavelength, just slightly off, and that's why we get in some spectra line spectra wavelengths that are very close together in these emission and absorption spectra. All right, so if these are different energies, how do we actually fill electrons? So let's say we have carbon. How does nature decide where the electrons go in carbon? I'm going to give you 3 rules to figure this out. The first is the Aufbau principle. And this just is what we said before. Electrons want to go to a low energy orbit unless they're excited by absorbing a photon. And the lowest energy orbital is going to be the one with the lowest n plus L value, right? So you can have 2 electrons in the 1s orbital. Then when you go to the n equals 2 shell, you can put 8 electrons in there, but you're going to fill the 2s orbital before you fill the 2p orbital. The next rule is the Pauli exclusion principle, named after Wolfgang Pauli, who came up with it. And the Pauli exclusion principle says that you can only have 2 electrons in each orbital, and that each electron has its own unique quantum numbers. The third rule you're going to get is Hund's rule. And Hund's rule is that electrons fill all degenerate orbitals singly before pairing up. So these electrons like to have their own orbitals if they can. So the electrons do have some favorable interaction through the magnetic coupling that can happen, or the pairing that can happen. But if they can avoid that pairing, they will. If they can go to a low energy orbital that's degenerate, they'll pop over instead of pairing. And a little caveat to Hund's rule, or an add-on, is that all of your unpaired electrons have the same spin. And we generally just say all unpaired electrons have an up spin, though that's just for simplicity's sake rather than from a scientific reason. All right, now as we start to fill our orbitals, it's really useful if you can figure out how to use the periodic table as a cheat sheet for this. So the periodic table looks like this, right? Though on here, I'm just showing the orbitals in each region rather than the elements themselves. And so over here on the left part of the periodic table, we have what's called the S block. This green region over here is the P block. You'll notice helium up here is actually in the S block, but we generally put it over here because it's a noble gas that's not very reactive. So we've got our P block, then our transition metals are our D block, and then down here is our F block. And I'll try and show you how to fill this. And we're going to have to do a little bit of jumping back and forth between a periodic table and the PowerPoint presentation, but we will do our best with that. Now let's talk about how we write electron configuration. There's two main ways. There's SPDF notation, or there's an orbital diagram notation, or what I call box notation. So for SPDF, what you're going to do is you're going to write the value of n for each orbital, or each subshell. So in this case, for hydrogen, it's got one electron, and so it's going to start by filling the 1s orbital. And since hydrogen only has one electron, we'll say that there's one electron in there. So we put our value of n, our value of L, and our number of electrons in that subshell. So for helium, it has two electrons. Those are both going to go into the 1s orbital. So we'll write, or 1s, orbital. So we'll write 1s2. Now in our orbital diagram notation, instead of writing out letters and numbers like this, we're actually going to just draw a box. So in this box, you'll notice we'll have one electron pointing up, one of them pointing down. And these electrons then correspond to a spin down and a spin up electron. So this is the box diagram for helium. So we'll draw a box for each individual orbital, and then we'll denote which orbital we're talking about down here. All right, now let's start working through this, and we'll give you some examples so that you can see what electron configurations actually look like. We'll start with lithium. So if we look at the periodic table, I'll jump over there real fast. If you look, lithium is the third element on the periodic table, right? So it's got 3 electrons. And if we think of the periodic table as a map where we have our S block, our P block over here, our D block in the middle, and our F block down here, then we can figure out real easy where the electrons are going. So lithium has 3. It's going to put 1 in a 1s orbital, its second in a 1s orbital, and its third in the 2s orbital. Right? So this line is the 1s orbital, 2s, 3s, 4s, 5s, and so forth. Right here is the 2p, 3p, 4p, 5p, etc. Now the tricky thing is that the Ds, even though they start 4 down, start at 3D. So these would be your 10 3D electrons. Then you have 4D, 5D, 6D. And then down here you have your Fs. And the Fs actually start up here with lanthanum and run all the way over to number 70, YB. And then LU actually starts your D block. So from LA down to YB, this is your 4F orbital. And then from LU over to HG, which is Mercury over here, that's your D block again. All right, so what does lithium look like in terms of its electron configuration? Well, let's jump back over here and we'll write it out. So it's 1s2, 2s1. It's got 3 electrons, it's got 2 in the 1s and 1 in the 2s. What does the box diagram look like? Looks like 2 squares right here. We filled our 1s with 2 electrons and our 2s with 1 electron. You'll notice here that the arrows, we have one pointing up and one pointing down, and these are half arrows, and we often denote electrons as half arrows just because it looks really nice. And then in the 2s orbital, we have only a single electron, so we draw that spin up. Now let's go to carbon, and I will jump back over to the periodic table now. You'll notice carbon is the 6th element here, so it's going to have 6 electrons. It's going to have 1 in the 1s orbital, a second in the 2s orbital. It's going to have its next 2 in the 2s orbital, and it's going to have 1, 2 in the 2p orbital. So its configuration is going to look like this: 1s2, 2s2, 2p2. Now let's draw its box diagram. It's going to have 1 box for 1s, 1 for 2s, those are full. And now for the 2p orbitals, you'll notice there's 3 2p orbitals, right? The 2px, 2py, and 2pz. And those are degenerate orbitals, so they all have the same energy, So we draw them all touching each other. And we start filling with electrons from the left, because in English we read from left to right. So we put a spin-up orbital in the first, or a spin-up electron in the first orbital, a spin-up electron in the second. Now let's go up to neon. I'll jump back to the periodic table here. Neon is our 10th element on the periodic table. So it's going to have 1, 2 electrons in 1s, 2 and 2s, and then 1, 2, 3, 4, 5, 6 in the 2p orbital. So its electron configuration is going to look like this: 1s2, 2s2, 2p6. Its box diagram is going to look similar to carbon's, but you're going to have some extra electrons in there. Now for bromine, bromine is the 35th element on the periodic table. And here we're going to start getting a little tricky. So bromine's right here, number 35. So we're actually going to have to go through the 1s orbital, the 2s orbital, the 2p orbital, the 3s, the 3p, then the 4s. And then what do we do here? Well, now we have to drop down to the 3d orbitals, and then we can pop back up to the 4p orbitals, right? When I say pop down, I mean we're dropping to a lower energy level. Let's jump back over to our slides. And so bromine's electron configuration is going to go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then it's going to go back down to 3, so 3d10, and back up to 4p5. And it's going to have a really long drawn out box notation here. You'll notice it's getting really long. And if we go to something like platinum, we'll jump back just one more time to the periodic table. Sorry if you're getting whiplash from the way we're doing this. But platinum is number 78 here. So it has to go through the 3D, 4P, 5S, 4D, 5P, and the 6S. And then right here at lanthanum, it actually starts the 4F series. So 4F through YB. And so then we have 14 4F electrons. And then from LU over to platinum, we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in that 5D shell. So our electron configuration is going to look like this. Now you'll notice this is getting really long. If you're having really a lot of trouble following what I'm saying about how to read the electron or the periodic table, make sure you talk to somebody and get help on that idea, because it's really important. And so if what I'm saying is not making sense to you, keep working on it until somebody says it in a way, or until it makes sense to you, okay? Because it's really important. As you go on to bigger elements like uranium, though, this coding for the electron configuration keeps getting more and more elongated, and there's just a lot of information there. And so there is a better way to do this, a way to shorten this up. And that is by using the electron configuration of a noble gas as shorthand. What I mean by this is, if you think about a big element like bromine, number 35, well, it's got a lot of lower electrons that have an electron configuration similar to a noble gas, right? So let's look at bromine on the periodic table real fast. So bromine right here, 35, it's got all this electron configuration behind it, right? But up until its 18th electron, that electron configuration of those first 18 electrons are the exact same as the electron configuration for argon. And so we can simplify this, the electron configuration for bromine, by putting argon in brackets, and that just means everything that's in argon's electron configuration is also in bromine's. And so if I jump back to the slides, we can write bromine's electron configuration like this, where we just default to the noble gas that's before it on the periodic table. So the nearest noble gas that weighs less than the element we're talking about. So for platinum here, you'd have xenon as the next noble gas down. For uranium, it would be radon. And you'll notice with this shorthanded abbreviation, bromine and platinum have about the same length in writing, right? They have different electron configurations, but it takes about the same amount of length, even though they're at very different places on the periodic table. And we actually get a slightly shorter electron configuration for uranium. All right, let's practice this. And for this, I will just let you use the periodic table, and then when I explain the answer, I'll jump over there. All right, so what is the electron configuration of this element? Go ahead and pause here to figure it out. All right, we're dealing with xenon, and then we're going to go 1, 2, 14, 10, and 2, so that's 24, 26, 28 elements past xenon. So let's jump over to our periodic table. We'll find xenon right here, it's number 54, and then we just have to go 28 past that. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. All right, so it's 82, so it's actually lead. Another easier way to do that is to recognize that the last electrons there are 6p2 in our electron configuration, so we could actually have just jumped down to the 6th row and there are p orbitals and gone in 2 electrons over here to our lead. So if one of those explanations makes sense to you, go ahead and use it. So our answer here is lead. All right, now let's get into the idea of core versus valence electrons. When we say core electrons, we're talking about electrons in filled shells. We're not just talking about the n = 2 level. Sometimes we're talking about the n = 1 or n = 2 or even up to the n = 3 level. So as long as those shells are full of electrons, we call them core electrons. And then our valence shell is our outermost shell, and our valence electrons are the electrons in our outermost shell. These are the electrons that can react. And so the word valence actually comes from a German word meaning combining power. The reason we call it combining power electrons or valence electrons is because these are the electrons that do all the work in binding one atom to another. It's what causes molecules to be formed. And so we call it combining power because they combine together. So if I ask, how many valence electrons does bromine have? To figure this out, I'm going to need to write out its electron configuration. And it's perfectly fine to do this with the noble gas abbreviation here. So bromine has an electron configuration of argon plus 4s2, 3d10, and 4p5. So how do we tell which one is unfilled? Well, 4p, that subshell can actually hold 6 electrons, but it's only got 5. That means that the 4p subshell is not full, so those are valence electrons. But you'll notice that the valence electrons are in the outermost shell, not the subshell. And the shell here, of course, is referring to the n value. So everything that has that same n value as these 4p5 electrons are also valence electrons, which means the 4s2 electrons are also valence, right? Because they are in this n = 4 shell. The 3d10 electrons actually count as core electrons because they're at a smaller shell. See how you do with this one. How many valence electrons does iodine have? So iodine is number 53 on the periodic table. Go ahead and pause the video and try and figure this out. All right, so iodine's electron configuration can be written like this. We put krypton in brackets because it's the nearest noble gas. And then beyond krypton, we have the 5s2, 4d10, and 5p5 electrons. So the 5p orbital, or subshell, sorry, is not full. And so n equals 5 is our valence shell. And so this actually works out to have 7 valence electrons, just like bromine. And actually, everything in that column with bromine and iodine, so fluorine, chlorine, bromine, iodine, antimony, and whatever element 117 is called, these are called our halogen gases, and they all have 7 valence electrons in their natural state. All right, so that is filling our shells. That's figuring out our electron configuration. There are about 8 exceptions, and fortunately, you only have to memorize 2 rules, and then you can find these 8 exceptions. And these 2 rules are actually very similar to each other, so you can almost think of this as thinking of one type of exception here. So if we look at our periodic table, if we start with our transition metals, so we're looking at the first D block element, which is Sc, then it's got 1 electron in the d orbital. And then we go to the next one, it's got 2 electrons in the d orbital, the next has 3 electrons, but chromium, the 4th element in the d block, actually does not have 4 electrons in its 3D subshell. It actually likes to steal 1 electron from the 4s subshell and pull it down into 3d5. And so now we have a maximized number of unpaired electrons, and we have a half-filled subshell for both the 4s and the 3d subshells. This is just a special case where this actually works out to be lower in energy than the 4s2 3d4 configuration, or this crossed out configuration. So going on though, after this, the next element has a 4s2 3d5 configuration, right? So it looks like we go 1, 2, 3, 4, 5, but instead we go 1, 2, 3, 5, 5. Then the next element has 6 electrons, then 7, then 8, and then not 9. Here again, so the 3D subshell can hold 10 electrons. So with chromium up here, we pulled down one of the s orbital or electrons to fill our 3D subshell, or half fill it. And copper here will do the same thing. It'll pull down an electron from 4s to get a filled subshell. So the rule here is if your transition metal just needs to steal 1 s electron to get a half-filled or a totally filled subshell, or a 3D subshell, it'll do that. And if I jump over to the periodic table, I'll show you where these are. So these are our elements 1, 2, 3, 4 in. So all of these guys in the 4th row of the D block, and then all of them also at the 9th, or sorry, not 4th row, but 4th column in the D block, do this where they'll steal an electron, and all of them actually in the 9th column, so from copper down. So if you can remember these 2 locations, they like to have a half-filled subshell or a filled subshell, then those, so you need to remember those 2 rules. All right, so go ahead and grab your periodic table and try and give me the electron configuration of molybdenum, which is MO here. Pause the video and figure that out. All right, so if you look on the periodic table, you might think that molybdenum has an electron configuration like D, where it's got the krypton and brackets, then the 5s2 electrons, and then the 4d4 electrons. But based on that rule we just learned, if you've got 4d4 electrons, or specifically 4 electrons in a D subshell, then your element is going to want to steal one of your electrons from the s orbital, and so you'll get a configuration like this. Now, what do we do for ions? Knowing the electron configuration of an atom will actually let you predict the electron configuration for ions, where we've gained or lost electrons. The general rule here is that elements want to either gain or lose electrons so that they can be like the noble gases, so that they can have a full valence shell, so that they can have 8 electrons in their valence shell. And when this happens, we say they're isoelectronic, where they have the same electronic configuration as the noble gases. So let's see what this actually looks like. So I'm not going to jump to the periodic table for these, but for sodium, its electron configuration looks like this. It is one electron pass looking like neon. And so it'll actually give up that electron to go to sodium plus and just have the same electron configuration as neon. For calcium, it's just 2 electrons away from argon's electron configuration. So it'll lose those 2 electrons to become calcium 2 plus, and it'll be isoelectronic with argon. So everything on the periodic table in the same column as sodium likes to lose 1 electron. Everything in the same column as calcium likes to lose 2 electrons. Now aluminum, it's in the first column of our P block. It is 3 electrons away from being like neon. It only has to lose 3, and it'll do that to form aluminum 3 plus. It'll look like neon. Now carbon is kind of funny. Carbon is 4 electrons away from looking like helium. So it could lose 4 electrons and look like helium, or it could actually gain 4 electrons and look like neon. So what carbon actually does, though, is it doesn't really do anything, or either of those. It likes to rather share its electrons and form bonds. And so that is actually the fundamental reason, or at least one of the very important reasons why carbon is such an important compound for life and for forming so many of the structures that we see. So it does not give up or gain electrons, it just shares electrons. Next we have phosphorus. Phosphorus is 5 electrons past neon, but it actually only needs 3 more electrons to look like argon. So instead of giving up electrons, if it only needs 3, it'll gain those 3. It'll usually steal them from somebody like calcium or sodium that's willing to give them up. And so now we have a negatively charged phosphate that's isoelectric with argon. Oxygen is a similar story, but it's only 2 electrons away from looking like neon. And so it'll gain 2 electrons, become O2 minus, and be isoelectric with neon. And the last one, bromine, only needs 1 electron to look like krypton. So it'll gain that electron and become isoelectric with krypton. Isoelectronic. Now for transition metals, I actually think transition metals are kind of fun with this. Because with transition metals, there's actually not usually a single right answer. There's often 2 or 3 right ways that they can give up electrons. So first, they generally lose all of their s electrons. And then they may or may not lose some of their d electrons. And then they often try to achieve a full or half full or empty d subshell. And so those are some of the goals that you have to keep in mind. Now it sounds like this will be fairly tricky, but it's really not too bad. So for example, if we write the electron configuration for iron right here, this is its box notation, and notice I'm just looking at the 4s and 3d orbitals. So in this case, the 4s electrons are valence electrons. And so iron will gladly give up its valence electrons to form the iron 2 plus ion. But you'll notice now it's also really close to having a half full 3D subshell. It could just give away that extra electron and become iron 3 plus and have an electron configuration like this. And it turns out that iron actually likes to do both of those things. And so iron 2 plus and iron 3 plus are actually both extremely abundant on our planet, both in your body and out of your body. And these molecules are essential, or sorry, these atoms are essential for carrying oxygen through your blood. All right, so let's look at a couple more examples. For titanium, it has an electron configuration like this, where it's got 2 electrons on the 4s orbital and 2 in 3D orbitals. So its box notation is going to look like this. So titanium can either give up its 2s electrons, or it can give up its 2s electrons and its 2d electrons. So it can form either the titanium 2+ or the titanium 4+ ion. And it does those both readily. Now looking at that, you would not be able to predict that the titanium 4+ ion is more abundant. Titanium 4+ is more abundant, but again, like I say, you wouldn't be expected to know which of those two is more abundant. Then we've got nickel. It's got an electron configuration that looks like this. And so nickel can give up its 2 electrons in the s orbital. It can also give up its 3 electrons in the d orbital, but that sounds like a lot of work. They're already paired. Why even bother? And so nickel generally just forms the 2+ ion. So if it's going to take a lot of work to rip apart these pairings and get down to a half full shell, it's just not likely going to happen, right? Really, once you have 3 electrons, it's just not worth it to strip all those off to form another ion. Now, copper is a fun one because copper, like we said, can steal an electron from the 4s orbital and bring it down to the 3D subshell so that you have 10 electrons or a full subshell at the 3D level. And so copper actually has these 2 different possible electron configurations where you have 2 s electrons or you only have 1. And so copper can actually undergo both of these losses, and it can form copper 2+ or copper plus. And ironically here, the copper 2+ is the more abundant. Again, you wouldn't have to be able to know that by looking at the electron configuration, but you would be expected to make a reasonable guess as to which electrons are formed. For zinc, it's got a full s orbital, and it's got 5 full d orbitals. None of these electrons in the d level are going to go away very easily. You got to really rip them off. And so zinc is just going to lose those s electrons to form the zinc 2+. Right? So the rule is you always ditch your s electrons, and then you can lose your d electrons if it'll get you to a full, half full, or empty d subshell. And the more electrons you have to rip out, the harder that's going to be. Right, silver is similar to copper in that it's got these 2 electron configurations, and so it can lose its s electrons. And for silver, interestingly, the 1+ ion is more abundant than the 2+, whereas copper, that had a similar valence electron configuration, its most populous ion is the 2+. All right, now let's get down to magnetic properties. So magnets are actually controlled by these electrons and their configurations. So we'll talk about each of those and give some examples. So there's 3 types of magnetism that we talk about. The first is diamagnetic, and in a diamagnetic material, all of the electrons are paired. So zinc 2+ is a good example of this. And interestingly, diamagnetic, this is what we usually think of as not magnetic, right? A way to remember that. So di, or dia, means 2, which you can associate with paired. The other is dimagnet, as in it's a dead magnet, as in it's not a magnet. It's one way I remember it. But diamagnetic things, or things that we think of as non-magnetic, are actually slightly repelled by magnetic fields. So this repulsion is so small you can't normally feel it. But if you actually get a really strong magnet and put a diamagnetic material above it, it'll float. You can even take a large thing like a toad, and scientists have even taken a toad and set it inside a really strong magnetic field, and the toad just floats and wiggles around. Doesn't seem to be very happy with it, but it's funny. Not because it's mean to the toad, just because you made a toad fly. Now, the next type of magnetism is paramagnetic. And this is magnetism that is susceptible to magnets. So things like metal that will stick to magnet. And in a paramagnetic material, you have at least one unpaired electron. And so this is things that are attracted by a magnetic field. So typically we think of metals, but it turns out things like oxygen gas and liquid oxygen are also attracted to magnets. So here is some liquid oxygen suspended between two magnets. And so in a paramagnetic material, you have to have at least one unpaired electron. And then when those unpaired electrons interact with a magnetic field, they can all align towards the magnetic field and stick to it. And the last is a ferromagnet or ferromagnetic material. This is what we actually think of as magnets. So like a fridge magnet or any other magnet you might have seen. And in a ferromagnetic material, you have unpaired electrons spontaneously align their spins with an outside external field. What this means in layman's terms is in a ferromagnetic material, you have multiple atoms with unpaired electrons, and all of the electrons in the entire material have their spins aligned. So not just in one atom, but the electrons in multiple atoms are all aligning their spins with each other. And so this is what creates our actual magnetic field and gives us our normal fridge magnet or any other type of magnet you've dealt with. All right, let's see how you do with this last idea by asking which of the following is diamagnetic. Go ahead and pause here and try and figure this out. All right, so diamagnetic, dia means two, or which is associated with pairing. So we're gonna have to pick one of these materials where all the electrons are paired. There's only one electron in this 2s orbital. One electron can't pair itself. Now down here, these ones, oxygen and titanium, they have even numbers, but that doesn't mean all the electrons are paired. So for example, for oxygen here, oxygen is going to have 4 electrons in p orbitals, but there's 3 orbitals. So we're going to put 1, 2, 3 electrons. So we'll put 1 in the px, 1 in the py, 1 in the pz. We have 1 left over, and we will flip that one over and have it be a spin down in the px orbital. For titanium, it's a similar thing. We have 2 electrons in d orbitals, but there's 5 d orbitals at every n value. And so we're only going to put 1 electron in the first orbital, 1 electron in the second orbital. So it's not going to be that one either. They're not going to be paired up. So it's only here where we have our 4s2 3d10, where all of our subshells are filled, that we are actually going to have unpaired electrons. So the electron configurations for each of these are going to look like this. And so zinc then is going to be our diamagnetic material. Remember, dia means 2, which is paired. Paramagnetic, you have at least 1 unpaired electron. And then ferromagnetic, you have unpaired electrons in different atoms aligning with each other.